Hello everyone, so welcome back. This is part 5, which will be discussing the statistical edge. So the key goals here is that we're going to learn some key matrix algebra operations which are fundamental for building our model. We're not going to learn the whole subject of linear algebra. I do recommend to take like a linear algebra course. Maybe I'll put like there's a really fantastic video series that I can send, so you can, if you want to learn more about linear algebra. But the key goal really is how to create and measure a statistical edge. And also another really important goal is to show how you can make money with just a very tiny statistical edge. And the key lesson there is like the win rate does not equal the alpha. And then we're going to actually build our first alpha model as well. So the whole series so far has gone from like learning one-dimensional arrays, vectors, and operations that are based on arrays. Then we've gone into time series, and now we're going to go into matrices. With matrices, we can model multivariate, so that's multiple time series at once, because with our models, it just won't be just like one time series. We maybe want to model like several time series. So we need to be very comfortable working with matrices. And once we're comfortable with that, then we can actually do like forecasting, predictions. And just the key goals of this series is to develop knowledge, domain knowledge for building models. And with the models, that's how we create our statistical edge. And then the strategy, then we'll go into the strategy, which is how to execute the statistical edge. So we're going to go into these. We're already now tackling models, but then we're going to go into some more model topics and then go into strategy. So the first thing we need to do is to import our libraries. So we've got here again, we've got NumPy, which is for numerical computing. It's just very fast vectorized calculations. We've got our data analysis library, pandas. This is our data visualization library to plot some data. And then our machine learning library. And so we're using pytorch, and I've had some feedback as well saying, well, why use pytorch? It seems way too like you can just use like scikit, and that's a valid point. But with the machine, like for example, we can just build like a linear regression in Torch, and it gives us so much control over the whole process of training. So like for example, if we were researching to find out what's the best way to build a profitable model, we want very fine-grained control over the whole process, and pytorch gives you that flexibility, that low-level API, but it's still very like Python code, and you can like still just write like a machine learning library in like just 10 lines of code. Anyway, so we need to now discuss matrix algebra. So I'm going to go over this quickly. So this is only just purely a subset of linear algebra. I'm just teaching you just the bare minimum, just so you can understand the key operations of machine learning. And so we need to just go over like what is a matrix. And a matrix, essentially, in terms of code, is just a two-dimensional array. So for example, this is like a matrix here. And I'm just going to 5, 6, 7, 8, and 9. Okay, so this is it's essentially just a two-dimensional array when we think about it in terms of code. And for example, if we want to access like the first element, so this would give us it gives us an array. So to get like an individual element, which we call like a scalar, then you would have to also then index it again. So then we can get like 0, 1. If, for example, we want to get just the other elements, then we can do it like this. So it's a bit tedious, but then just to make it crystal clear, so then it's 2. And if I want to do it for the next one, and so forth, and I could even do it for, like, for example, we can then go into the next row. Okay, so that's a matrix, okay, and there are some very important operations that we need to be able to do, and one of them is to do what's called matrix scalar algebra. So I'll just write this down: matrix scalar algebra. And we've already discussed like scalars in previous videos. So for example, essentially what we want to do is, like, for example, in this example, we want to do matrix, like whatever. So for example, here, this matrix, we want to add 1 to it. If we're going to do it manually, we would have to do something like this. So we just say, like, okay, the number of rows is the length of the matrix. Oh, it's nice that it's auto-completed. And so we want to work out what our M is, and so we'll just do this. So in mathematical notation, you'll see like a matrix being defined as like M or N. So for example here, like number of rows. So when you see it like in mathematical notation, then this is essentially what it represents. And like to do this, we can loop over range of M, and then for J in range of N. Okay, and then matrix I J. So this again, it's 2-dimensional, so we need to get to the individual element, and then we're just going to add 1 to it. Okay, and then we're just going to print out the matrix. So you can see here, like it started from 1 and now it's done plus, but this is like extremely tedious if you're having to do these like operations. So, and I'll just show you like essentially what essentially it's done, just to make it super crystal clear. So that's essentially the operation that it's done. So it's just added 1 to each individual element in the matrix. But you don't, there's 2 reasons why you wouldn't do this, because it would be extremely tedious and unproductive to write these manual loops, and also in terms of performance this would be terrible. So for example, NumPy has like specialized code to do matrix operations extremely fast, and this is again factorization. So for example, we can do this. We can do, for example, we can so exactly the same code. I'm now just going to represent it as a NumPy array. Okay, so if we now print out A, so you see this is like an array, and it kindly displays it in a more matrix notation. So that's the matrix, and what's really nice is that instead of having to manually do the loops, there's a really nice abstraction that we can just use like mathematical notation, which is just like, okay, so you can just treat this, and this, it gives us exactly the same, see here, and it's way much faster as well. So imagine this is like a huge matrix. The performance difference is night and day. So, and then also as well, there's like this just a very important part is like this associativity. Okay, and we can also do like multiply as well. So you can see here, but that's matrix scalar, so that's an important operation, and the most important operation is the matrix vector algebra. So we need to be able to multiply a matrix by a vector, and this is very fundamental because essentially we're gonna be doing this, which is like x multiplied by our weights, and so x is our matrix, and we need to multiply it by a vector which is our weights, and we want to make a prediction, and the prediction is the y-hat. So we'll have a matrix, even if it's univariate, we still need to model it as a matrix. So this is like the very fundamental operation. So it's important that we understand the mathematics and the algorithm behind it. So again, we're going to use NumPy. So for example, here I've got, we're just maybe just print it out. So we've got a matrix here of, let's say, log returns, and we've got some weights. And let's just say we've used machine learning to work out the most optimal weights. And then we're just going to define that. I'm just going to show this. Okay, and essentially, what we want to do is what's called like a dot product. Okay, so we take the x, and this is essentially matrix multiplication with a vector. Okay, so then, and this gives us the predictions for each row. So it's it's multiplying each of these two elements with this and summing them up together. So essentially what it's doing is it's doing this. Maybe if I just copy and paste, it'll be quicker and easier. And you can see this is exactly the same. So I'm just putting the individual weights 1 and weight 2. So imagine these as like lag 1, this is lag 2, okay? So with lag 1, this is the weight for it, and for lag 2, this is the respective weight for it. So it's just multiplying this, say, make it more concrete, this is say log return, we're multiplying it by this weight, and plus the value, the lag 2 value, and multiplying it by weight 2. So that would be our first prediction, and this is our second prediction, and then our third prediction. So this is like very fundamental for machine learning. And then also we add like remember that we add a bias, and so I'm just going to put this here. But in a mathematical notation, this would be like a B. And so essentially, like our model is going to be, the mathematics of our model is this. Is we're going to do a dot product between x and our weights, which is what we're going to work out as like what's the optimal weights, and then plus the bias. So essentially we're just adding, you see what the bias just does, it just adds this tiny, like say epsilon number to it. And so for example, this could be just a very tiny negative number, but the bias could skew it to be turned into positive. So and also as well, if let's say if it, if it's this dot product is 0, then essentially it's just the bias. And so, but there's a very important operation, distinguishment, which is broadcasting does not equal. Okay, maybe broadcasting does not equal matrix multiplication. So a really common gotcha, I would say, is this. So for example, you may be tempted when to do this, and this is not matrix multiplication, even though this is the multiply sign, but this is something called broadcasting, and this is like totally different. So just got to be careful when you're, for example, the API that you're using to represent your matrix, that you're actually doing matrix multiplication and not broadcasting. So for example, in NumPy, this is how it's done. So now we just understand some very basic fundamental operations of matrices, and now we can sort of go into, dive deep into machine learning. And so now the next part is, which is I'm just going to, if this comes up, is we're now going to work out how to develop a statistical edge. Edge using machine learning. Oh, I can't see. Okay, and maybe if I put another text in here. So the idea is that we're going to predict a future log return, and so essentially the statistical edge is the, oh, maybe I'll just copy and paste this because this is the following, right? Is this, that the statistical edge equals like a good forecast. So, and essentially it's like where the expected value is positive, but we'll go into that in more detail. So the first thing we need to do is to download some data. So what we're going to do now is download some what's called open, high, low, close prices. This is just a very, very basic data set, but I just wanted to show, just like with a basic data set, you can still make good predictions. So we're going to download the perp data, and so we're going to use Bitcoin dollar perp contract. It's like a future. It's essentially like it's like a futures contract that doesn't roll. And the futures are great for speculating because it gives you a very quick ability to bet if the price is going up or if better going down, and you can also leverage. But there's a bit out of scope to go into the details, the mechanics of a perp contract. But so now we're just going to download the data and load it into a pandas data frame. So, and this is an hourly time series. So you can see here, like each row represents an hour, and you've got the open price. That's the price it starts at, and then the highest price it reaches in this time period, and then the lowest price it reaches, and then the price that it closed at. So at just right at the end of this time period, just before the first hour here, then it closes at this price. And this is the trading volume for that respective time period. So that's the what's called OHLC data. It's just a very basic data. Most like firms will be using high definition, high frequency order book data and trade feed data, but we're just going to just want to show that even just with a very basic data set that we can still develop a statistical edge. So the first thing we need to do, which we've already discussed in previous videos, is to create the log return. Okay, so this is I'm not going to go over it again because I've done it in previous videos, but essentially we want to measure the log returns because they have this property called time additivity, and they can also model compound growth rates. But yeah, this is just I just recommend if you're interested, just look at an econometrics book, and it will explain in more detail. So that's now we've got the log returns, and now so this essentially what we want to predict is we want to predict this closed log return, and we're going to predict using the previous log returns. So this is what's called like an in econometrics is what's called like an autoregressive model. So what we're essentially looking at is so what we're doing here is we're just shifting the data to say, okay, lag 1. So for example, what ideally what we'd want to do is, like, say, using this lag, say like lag 1, we want to make a prediction to predict this log return. So this is the price movement, the actual price movement, and that was the previous price movement. So we want to predict the price movement, this one, from this previous log return, and that's essentially that this came from the previous one. So for example here, the price return was this, okay, this number, and you can see this now for the next time period that it's now the lag 1, and then for the previous one in the next future time step it's now lag 2. So that's essentially what we want to do. So essentially what we're predicting is, like, if we buy at this time and then close it just before the next time step, what's our return? So that's essentially what we're modeling, okay? And we're just going to look only just 3 lags to the behind. You could actually like do even more. And so if we just look at the correlation, so we in the previous video we discussed correlation. Okay, so if we now look at the correlation here, so we've got these like lags, and you can see what's quite interesting is like it's not decaying. So for example, the strongest correlation here is actually lag 2 and not lag 1. But you see this is negative, so this means that when lag 1 goes up, then closed log return typically goes down, and vice versa. Okay, so and now I want to do is just to inspect visualize the data, because I just want to show you essentially what we want to do. And to do this, we're going to inspect the data. Okay, this might just take a while. And so this plot is going to show us the distribution for each variable here. So we're going to see we've got closed log return, and then the lag 1 and lag 2 of it, and then lag 3. And you can see here that it's plotting the relationship visually, the relationship between say log return and its previous lags. And you can see here that there is really no what we call there's no polynomial that we can model to represent this. There's no clear okay, this is a linear relationship, okay, this is a quadratic relationship, or this is there's no polynomial that we can it's so obvious that we know okay how to model this. So this is the problem with financial data. It's extremely noisy. So this is why, for example, linear regressions are quite good, because it just makes the decision space, to buy or to go long or to go short. It's a linear curve, so it's a good approximation with the presence of noise. So that's and also here as well, for example, this is, you can see here that there's only one peak here. And unfortunately, you can't see other properties of the distribution here. For example, in the previous video we looked at the central tendency, and then the dispersion, the standard deviation. But then there's other what's called moments, which is for example kurtosis, how fat are the tails essentially of and that essentially models extreme events. And then there's also a skewness, which is okay, is the distribution skewing to one side? So is it more trend skewing more to let's say positive or negative? Anyway, so that's you can see a visualization and see visually why it's so hard to predict these log returns. So now we've discussed that. Now, for example, I just want to show okay, we're going to model a matrix. Okay, so from this is our values, and this will essentially turn into a matrix. So using the previous returns, and now we can see this is now in a matrix notation. So this is now ready to be passed into a machine learning model. And another important characteristic is to look at the shape, and the shape tells us the dimensions of the matrix. And you can even get it into three-dimensional matrices, which are essentially, or actually n-dimensional matrices, which are called tensors, but we're not going to cover those. And then, for example, now what we want to do is to create our vector of what we want to predict. So X is the model, the input, and then essentially what we want to do is predict this, and then we model this as a vector. And if we just look at the vector here now, you can see this is it's just a one-dimensional array. And if we look at the shape of it, you can see okay, for this to be able to multiply, you have to ensure that this has these two numbers match. But anyway, so now we're going to go into, so what we're going to do now is to do forecasting. So we're now going to predict the future log return, and we're going to do this, and we're going to do it via regression. So regression is where we predict a real valued number. So like it could be a floating point number, it can be an integer. And in the next video we're going to do is we're going to do forecasting, but using a classification, which is we're going to classify it being up or down. And with classification, it also gives you like an associated probability. But anyway, we'll discuss that in detail in the next video. So what we're going to do now, what's really important is to split, I'm just going to put it down here, to split training and testing data. And essentially we want in-sample data and out-of-sample data. And it's just very important that we do this in the correct way. So, and I just want to visually show you roughly what it looks like. So for example, with a time series, like for example, it's really important that you preserve what's called the temporal order, which is just the natural order of the time series. So what we want to do is to learn the pattern on, let's say that we've only got 8 data points. We want to teach our model using like the first 5 data values, and then we want to say, okay, is there persistence in this pattern? And we will then use for testing is so this is called in sample, this is out of sample. We want to test, does this pattern persist for future values in the time series? And it's really important because, for example, if I just taught or teached a model just on all this time data, I don't know if this will work into the future. So I don't know if this pattern is persistent or not, and especially because the data is so noisy. And this is another really important thing as well, is that we don't want to, for example, there's a library called scikit, and there's this thing called train test split. And be very careful using that, because I think by default it's to shuffle the data, and you do not want to shuffle time series data, because you'll get amazing results and you think you're a genius, and you think, okay, you go off to the races, you start to trade it, and then realize that you're like hemorrhaging money. And that's because of data leakage. Because, for example, if I mix the data, so for example, if I just like randomly picked like T0, T5, 6, 7, and I just tested on it would see data in the future that it would not know at that time. So it's always very important that if we're passing any data, that we don't have what's called data leakage. It doesn't see data that it wouldn't see in the future, because you're going to get these like impressive results, but it's purely done because of like a data leakage. Anyway, so that's just really an important step. And then, so for example, we can it's very easy to split by time, because that's essentially what we want to do. For example, we want to split it at T4 here. So at T4, we put this into train, and then the most recent for testing. And so, for example, we can just do it like this. So essentially what this code is doing here is we're passing our matrix, actually that should be X, and oops, and then we're deciding, okay, what ratio should our train size be, and then returns back this like tuple, which is the first part is the train, and then the next part is the test. So this is what we do. So we pass in our data frame, and we say, okay, our train size is 0.7. And by the way, this is what's called like a default value. So for example, I don't have to add this explicit value. It will just by default, for example, if I just pass in this, then by default it's just going to split it, like the test size will be 25%. So now I can just run this, and now I just want to show you like the underlying data now that I've split it. So you can see here it starts, the beginning is 2020 11/27, and then at the end of the training data is the 5th on the 24th. So, and then the most recent data that's the data that we're going to be using for learning a pattern. And then once it's learnt a pattern, then we want to test it. And we've got quite an extensive range of data here. So you can see here that's just 1 hour next is for our test, and then it goes all the way down to the 10th of the 11th. And so then that's what we're going to, this is our out of sample. And so now we've split it. Now we're actually go into the meat of developing an edge, which is to develop the train the model. And I'm just going to put this a train model. So just to make it, and a really important property that we need is the reproducibility, which is if I run this code and you run this code, it should produce exactly the same results. It shouldn't just be like you run it and then, hey, I get completely different results. And so what I'm going to probably do is I'll just copy and paste and then go over the code. And this is our machine learning, our training. So I'm just going to go over what does each one do. So we actually don't need to import the libraries, but anyway. So we've got the reproducibility settings. So we're going to set we need to set what's called a seed, and this just is to ensure that all the non-deterministic algorithms is reproducible. So we're just setting several big seeds here. It's just kind of overkill, but I just in case like you change anything, that's still reproducible. So we're setting the seeds here. If, for example, if we want going into GPUs or multiple GPUs, then there's this CUDA. There's another, like for example, in CUDA NN, there's this like deterministic flag that we can set, but we don't need this. And so so once we've got the reproducibility settings, then we actually want to start to create tensors. So with pytorch, which is the machine learning library we work with, it works with tensors. So even though we're still working with vectors and matrices, it needs to be treated as a tensor object. And so essentially what we need to do here is define what our input feature is. And so we're just going to create a very basic model, just one input feature, and it's going to predict the log return. So this is the predictors, and this is what we want to predict. And we want to model this relationship as a linear regression. And then we need to split the data into pytorch tensors. So this is the code that does it. There's just one thing, just important detail that I need to mention here is this unsqueeze. We need, because this is just, we need to add this like column dimension, but otherwise it'll complain and say this is the incorrect shape. So it's important when you're doing like matrix algebra operations is that the dimensions are the correct size. So this is just to make sure that it adds this column dimension to it. And so now, and also as well, I just recommend is just to print this out like before the squeezing and then with the unsqueezing, so you can really have a good understanding of what it's actually doing behind the hood. And so now we need to define the model. So this is the number of input features, 1 in our case. So this is what we call like a univariate model, and we're just going to do a simple linear regression model. Especially if you're starting, you need to walk before you can run. So before you want to, for example, if it's an extremely competitive scenario, let's say market making, it would be advantageous to look at more complex models, because just squeezing a tiny amount of EV is game changing. Whereas, but for example, with our models, we just want to start with just something very basic, and it can still be very profitable. And there's actually quite a lot, because we're using pytorch, the way how we calculate the weights, there's a lot of alpha opportunity. Anyway, so now we're going to go, this is the model, and so this is this, it's already baked into pytorch, so we don't need to manually like create a model here. We can just represent it, this linear module here. And now we're going to use something called Huber loss. And Huber loss, so this is essentially measuring the loss between the error between our prediction and the actual value. And there's multiple ways to measure loss. There's like some very common ways, which is like mean squared error, and that's like squared difference, which is very sensitive to outliers. And then another very common one is what's called mean absolute error, which is where it's not sensitive to outliers. Which is you're not squaring, you're just taking like the absolute difference, and there's a balance between this. Is something called the Huber loss. So I recommend to Google it and look at the how it's defined. And again, if we're just using the scikit, we'd not be able to control like how we wouldn't have this great flexibility. So we're going to use something called the Huber loss. I really recommend it. It's a nice balance between mean squared error and mean absolute error. And we're going to use like a very basic gradient descent optimizer. So this is essentially how we optimize our model. I don't really want to go like, because I'm already spending quite a lot of time to go over the matrix, but maybe in a future video I'll just go over the mathematics of the stochastic gradient descent. But you could, if you just take a machine learning course, it'll cover this and probably do a better job than I could. And then you've got this thing called the learning rate, which is like this is what's called a hyperparameter. But we're just going to leave this the learning rate as this value at the moment. But if we're really like fine tuning things, then we can. This is one parameter that would be interested in optimizing. Anyway, so now we can go into the meat and bone of the training, which is the training loop. So essentially, I'm looping over, and there's this thing called an epoch. So after each time I go over we're doing what's called a full batch gradient descent. So we're taking advantage that all our data is in memory. But for example, if we're trying to build like a large language model, we do not be able to fit all the data into memory. So we would need to do like a small batch, essentially, like for example, only just 64 batches at a time, or 32. But because we've got all we can load all the data into memory at once, we're going to take advantage of that by using what's called a full batch gradient descent. And essentially what we need to do, because the gradient, accumulate, like it's additive, these gradients. So what we need to do is always just to reset the gradients so it doesn't accumulate them by default. So for example, if the gradient is 1 and it adds let's say another 1 to it, then it's not now 2. So it's just very important that we just zero out the gradient. And the gradient is essentially just how the process of learning essentially is. Anyway, so this is the most important part, which is our prediction. So we pass all of the training data into the model, and it makes the prediction for every data point, every row essentially in the training set. And it's represented here as a vector. And this vector represents for every row essentially in the training data, the corresponding prediction. And now now we're going to use the criterion, which is our Huber loss, to quantify the loss or the error between the actual values, which is Y train. So this is the actual values in the training set against our predictions, and to quantify that loss or the error. And then we need to do something called back propagation, which is we need to compute the gradients of the loss with regard to the parameters. So once we've done that, then we can update the model parameters using the computer gradients. And once we've done that, then that's the whole process done. And what we do is, like, for every 500 epochs, we're going to print out the loss, and then right at the end, we're going to look at our model and see what the final parameter weight is and what the final bias is. So if I run this now, this might take a while because I've probably been talking quite a lot, and hopefully it hasn't, the kernel hasn't restarted. Okay, here we go. Okay, so you can see here that the loss is actually quite high, and you'll see as it starts training that this starts becoming a smaller and smaller number. And in practice, typically you have, like, you want to okay, maybe I should discuss or not. Okay, there's a point in time where we want to stop, because then it starts to overfit, especially when we have models that are more complex, like a neural network. There'll be like a cutoff point where okay, it's overfitting, so it's not generalizing. So there's a certain cutoff point, and it's both like, to work out this, it's both an art and a science. So anyway, so that's the key machine learning algorithm. So it's it's only 1, 2, 3, 4, 5, 6, 7, like 8 lines of code. So it's not extremely complicated. So I just want to also do this, which is just to print the code out. It's just to show, like, the weight and the bias. And you see here that it has this requires grad. So this is represented as a tensor. And now that we also, another important thing to do is that, for example, if we want to reuse this into the future and maybe, like, deploy this into production, we need to store it onto disk. And so to store it onto disk, we can just call this torch.save, and this essentially, the state of the model is saved as a dictionary, and a dictionary is just like a hash map, or just, yeah. Anyway, it doesn't matter how it's stored, it's just that we store it. And now, because for example, we're like deploying it into production, we can then just, like, once we load up the trading system, we can just load up the model and then execute it. So now what we want to do is to evaluate the model. So, like, we don't know yet if this is a good model. Like, the loss measuring the loss doesn't tell us, like, is this a profitable model or not? So this is what we want to do we want to evaluate the model with respect to profitability out of sample. And remember that we're going to use the testing, the most recent data, to say, okay, does this pattern persist or not? And what we need to do is to add back the data. So we're going to do this. We're going to make a prediction using the model with its new with its parameters that it learned, the weight and the bias. Oh, I should maybe just point out that it's negative, and the beauty of linear regression is it's extremely interpretable. So I know I can look at this and I can say, okay, why has it decided to trade? And I can see straight away that because it's a negative number, then this is a mean reversion behavior. So for example, if the lag 1 is positive, then I know that the future log return is going to be negative, and vice versa. So I know because it has a negative weight, and that it's a mean. This is modeling some mean reversion dynamics. So now what we're going to do is look at the outer sample data. Okay, and we're going to have a look and see that it's a tensor. And don't worry about there's this gradient. That's we will remove that. So the next goal thing is to detach it. Y-hat detach. And I think it does probably explain it. Oh, it doesn't explain it. So when you detach it, you're going to remove this gradient from it. So now you can see that the gradient function is removed now. So, but we now want to, because we're going to add it back into our data analysis library, we want to convert it back into a NumPy array. And I just want to quickly just show you though the shape of it. So we need to do the reverse of the unsqueeze, and the reverse is to squeeze it. So what we want to do now is to squeeze. And we can see now, you can see here, this is like a row vector, and now this is a column, what's called like a column vector. Don't worry too much if that doesn't make too much sense. Just the most important thing is that you see that the shape is different now. So for example, hang on, my mouse is just not moving. So I just wanted to show the shape, because that will make it more clear and understandable. So now we've gone like the shape was this. It's now gone from 2-dimensional to 1-dimensional. So now we've squeezed it. And now that what we can do now is to add it into our testing data frame. So now we can see here, now we've added it to our test data frame data set. Okay, so we've made so we haven't. This is completely out of sample. Our model has not seen any data, the most recent data, so it hasn't seen this. So we can say that okay, it's, you know, and this is what gives us like, okay, does this pattern have persistence or not? So, and you can see here, for example, maybe I'll just explain it. So that's the actual price movement as a log return. So it moved down here, and it predicted it goes up by this amount. Okay, and so for example here, for the next hour, it predicted. So for example, we would lose money here because we predicted the wrong direction here. And for example here, we predicted that it went up, and our model predicted it went up. So we would actually make money here on this. So we need to create a column to know if we won or not, if our prediction is correct. And this is what's we need to say, like, what direction did we bet? Did we bet going up, or did we bet going down? So for example, we're now going to add what's called the directional signal. And another key important thing, because I'm talking in trading lingo, and I'm just aware that some people may not have any trading background, that for example, if we're gonna encode that 1 equals to go long, and to go long essentially means betting price going up. So if you hear anyone says, I've got a long position, that just means that they're betting that the price is going up. And then on the other side, if we're going to encode, it's either going to be -1 or 1, and that means to go short. And short is essentially you're betting the price going down. And with these future contracts, perp contracts, they allow you very easily to speculate both up or down without owning the underlying asset. But that's a bit out of scope. But what we're modeling what's called the perp contract, which is I think is much better than futures because they don't have this rolling property. But anyway, the key important thing is that one is to go long, -1 is to go short. And so now what we need to do is to encode this directional signal. So to do this, we're going to, maybe actually I'm just going to copy and paste it, be easier. Okay, so now that's our directional signal, and I'm just going to print out, and just to make it super crystal clear to see what it's actually doing.
So, and but essentially what we're doing is we're taking the sign, the mathematical sign of our prediction, and that tells us the signal that we're going in. So, for example, here we're predicting it's going up. So the directional signal is 1, and it actually went down, so we actually lost there. For example, here our prediction, like if we encode it as just the sign, is 1.0, and it actually does go up. So that here we actually did win, and vice versa here. Like for example, here this is the prediction is to go short, but actually the price went up, so we would lose money here. So we now need to encode did each individual trade win or not. And to do that, we're just going to, and this is what's called the directional accuracy. Now we're just going to do this, is to evaluate the directional accuracy. Okay, let me just take it. Okay. And it's very important, because you may see some papers, especially like econometric papers, that might just mention it as DA. And that's essentially, if you see any like my code or DA, then that's what we're talking about, is the directional accuracy. And to model, to quantify the directional accuracy, and essentially the directional accuracy is just the win rate. And so, for example, this is how we do it. So we're going to say is 1 equals the directional signal equals the sign of what we're trying to predict, so the closed log return. And now what we can do is just to go over Okay, so we've got like our actual values. This is what the target that we're trying to predict, the future log return. This is our predicted value of this. And we want to know like the encode the directional signal, and then we want to know has it won or not. So for example, here we haven't won because it predicted to go long and it went short. But for example, here we predicted to go long and it does go long. So that's, and then just see if there's a good example where it's negative and it wins and it's negative. Okay, yeah, here's a good one. So for example, here it's predicted the price is going down, going short, and it actually does go down. So it wins there. And you're going to see something very interesting now. So I'm now going to, all right, hang on, why is this not, okay. So this is a really interesting, and this is, you'll be shocked by this. And you may even go, okay, this is rubbish. I'm going to close the video and dislike it. So just bear with me, because if I show you the win rate or the directional accuracy, you can see here it's only 50.7%, so not even 51% it wins under the time. It's just a very, very tiny edge, well, yeah, a very tiny amount that it wins. It's like dangerously low, okay? So, but if we now, so for example, we just looked at the win rate and we just like, okay, I'll throw this away, it's rubbish, okay? But bear with me here, because you'll see that the win rate is not the key performance metric. You want to look at the expected value and then the scaling, like how many times. So you can have like a very tiny edge, but if you trade lots and lots of times, you can make huge returns. Anyway, so now that we've got the direction accuracy, and I'm just going to, hopefully you haven't closed down the video. And so now I want to do is to add the trade returns. So at the moment you're going to say, okay, something's a bit fishy here. So now what we need to do is to add the trade return. And the trade return is essentially what's the actual return that we make. And it's essentially we multiply the directional signal, multiply it by the target. So, and it'd probably be easier if I just show you the calculation it's actually doing. So for example, we're predicting it's going up and it's actually gone down. So we've lost money here. Maybe put is 1 as well, just to make it crystal clear. Okay, so essentially, if we've won, then this is going to be positive. So this means we've made money, and we're not. And a very key important thing is that we're working in returns, because then we can work out, okay, it's not like a concrete value like $10, or we can see, okay, how much money will we make if we invested like $100, $10, $1 million. So it's just allows us to know to model the scalability of it. So, and again here, so for example, it's false, then it's negative, right? So that's essentially what it's doing, because like for example, if we predict if the signal, let's see where, okay, so for example here, the directional signal is -1, and it actually has gone down. If you, and it's basic maths, if you multiply two negative numbers, you get positive. So this is why the trade returns positive here. Okay, so now we've modeled the actual, like on each individual, this is what's important, is this kind of round trip. So at the beginning of the time period, we open a position, and just before we close the position, before the next time series data point. So we just basically opening a position at the beginning of every hour, and then closing until before the next. So just literally just before, and you'd reopen with a new position. So essentially that's what we're doing. So that's the trade return, and now we need to evaluate the statistical edge, because this is the most important thing, because it's very, I don't know if it's just human intuition that we just always look at the win rate, because I don't know, it's just like, for example, there's like this interesting property that if you ask to guess a number between 1 and 10, most people choose like 3 and 7, and they're prime numbers, and this is just natural. So maybe it's just a natural reason that we look at the win rate. Okay, so now we're going to evaluate statistical edge. And to do this, we want to calculate the expected value. The expected value is essentially just the mean. And you can see here that it's positive, and literally just the heuristic to know if we've got a statistical edge is this. It's like, okay, is the mean greater than 0? And then that means we have a statistical edge. But there are some good statistical edges, and there's some bad statistical edges. Maybe that's for another video, but then we can just now, if we just print out has statistical edge, you can see it's true that it does have a statistical edge. So now what we want to do is to evaluate the total return. So for example, if we invested X amount of money, what's the total return that we would make? So that's the next thing we're going to do. Evaluate total return. And to evaluate the total return, we can just, because these are log returns and they have this property of that you can add them up together, then we can model the total rate. So here, the sum here is 1.03, and that's if we add up all these log returns. Remember, it's only just winning just 50.7% of its trades. And if we, for example here, and now what we need to do, because they're in log space, we need to convert them back into normal returns, or simple, what's called simple returns. And you can see here that it's a huge number. And so for example, if my initial capital, let's just make this code here, let's just say I start with very humble beginnings, right? And I just started with $100. And just to emphasize that, because I'm assuming majority are students. They're not going to, and also there's actually a capacity, because you can't just trade like billions on each trade, because your edge will be lost essentially. So there's like a capacity. Anyway, that's a bit too much details. But now what we want to do is to do this, which is to essentially just multiply this by our initial capital. And this tells us like, okay, why is it not? Ah, there we go. Okay, so you can see here that if we invested 100, we'll end up with $281. So it's not more than 2x, and there is a caveat to this. That we need to include fees. But for example, anyway, we'll discuss this later, but just see that's a huge amount, right? And it's very counterintuitive, because we're only just making like 50.7% win rate. And so now what we want, a very important metric, or just like say visualization or data analysis, is to evaluate the equity curve, which I'll put here. Now we need to evaluate the equity curve, and the equity curve is quite a good visualization, and we can model to see, like for example, these properties called like drawdown. But let's just go over. Okay, so I'll just explain what's going on here, right? So with log returns, it can model like if you reinvest your money, how much you make, and you get this like compound growth. So this is why the beauty of log returns, because we can model this compound growth. And so we do something called cumulative sum. So essentially, for example, for here, it just adds the, maybe if I show, is this log? Yeah, it is log returns. That it adds the previous trade log return. Actually, I shouldn't, it's a bit misleading, but this is not the trade log returns. This is the cumulative trade log returns. So essentially, it's just summing up the previous trade log returns at each time step. And then you can, at each time period, we can model the compound growth if we reinvest the money. And now what we want to do is to display this equity curve. So if I just go into here. Okay, so this is what our equity curve looks like. It goes into, so you can see it's going up, like even though it's only like winning 50.7% of the time, so just under 51% of the time, we've got this like sort of linear growth. So, and the key, maybe did I go into this? Did I show the? I haven't actually gone into. Yeah, okay. So I just wanted to go over like the calculation as to why. So I've gone over the statistical edge, but we calculated the mean. But I just wanted to show, like if we, the reason why is because it has a very tiny edge. Actually, maybe I'll do that in the future video. But essentially, our wins are just a tiny amount bigger than our losses. So just a very tiny statistical edge that we have here, and then this is why we have this. But there's one caveat to this, which is we haven't added transaction fees, and this is where we essentially was called piss on my bonfire, because this would be amazing, right? So in practice, this model can work. For example, if we have rebates, but I'm going to talk over that later. Just what I want to do though is, so this is the equity curve in log space. So this is, but I just want to show like in concrete. We usually rather, like say for example, if I invested $100, okay, what's the actual equity curve? So this make it more concrete, right? So we start 100, and you can see it like shoots up to like 150 at a certain time point. And I think this is where there was a huge crash. And so this model does well when there's like extreme price movements. but you see it like shoots up, right? So this is gross. We haven't factored in any transaction fees. And another important metric that we need to evaluate, which is the Sharpe ratio. And the Sharpe ratio is just like a model of like how much risk is there in this. And we'll just put this down, evaluate Sharpe ratio. And this is essentially modeling risk-adjusted returns, like what returns do we make per unit of risk. And then the maths behind it, maybe if I just copy and paste this, be easier. It's essentially just this. This is essentially informally what we're modeling. It's the returns over the risk. And we're going to do this. We can calculate it as just the mean over the standard deviation. We know what the standard deviation is because that's like a common measure of dispersion from the central tendency. So you see here, but the problem here is that it's in hour. This is like an hourly Sharpe ratio. It's not. We need to annualize it into annual Sharpe ratio, and to do that, we need to multiply it by like what's called an annualization factor. And annualize it because, for example, if I have a model that's say I'm trading in minutes, it's going to have completely different Sharpe characteristics. But we want to measure that like independent of the what we call like time horizon. So for example, we can measure it consistently between arbitrary time intervals, and to do this we need to do this annualization. And I'm just going to annualization. And I've had a few people mention me, say, hey, about, why do you do this? So I thought it would be a good time to explain it. So for example, this is exactly the same, but this is the Sharpe ratio for like on an hourly level, and we want it on an annual level because then we can just consistently measure it between like for different intervals, right? So essentially, we just need to do is to multiply it. So for example, we just need to work out what our t. So we do is we multiply it by the square root of t. I think mathematically is n, capital N, but that's more of a pedant observation. So the t here is essentially because we're trading. Like for example, we're trading perps, and perps you can trade 24/7 every day. So essentially, there's 365 days in a year, and because this is an hourly trading model that we're making a forecast every 1 hour, and we assume that we're going to trade every 1 hour, then it's 24. So RT is just the number of trading days in a year multiplied by the number of hours in a day, and that's RT. And then we just take the hourly Sharpe ratio and then multiply it by our annualization factor, and that's how we can analyze the Sharpe ratio. So yes, we are scaling the Sharpe ratio, but we're scaling it proportionally to our time horizon, so we can have it's just so that we can compare this against, let's say we go even more low, like predicting on a minute level, that we can consistently compare our trading model that's in hours against minutes in any arbitrary time scale, like for example with days. So that's the reason why we do it. It's not like a academic exercise. And just to piss on the bonfire is get really excited, think, okay, I can start trade this, and we haven't factored in the transaction fees and what's called like net returns. So and that's where you include the transaction fees. And it's quite common in some when I was looking at like academic papers at the time, was that some papers don't even model the transaction fees. And it's really important that we do model the transaction fees. And so what we're going to do, maybe if I just copy and paste this. Okay. So, and it really depends on what type of, like, so for example, we could actually use this model So for example, if we were like running this as a making strategy, which is essentially we're adding liquidity, not taking away liquidity, the fees are usually lower. And let's say we have a really good relationship with them. Let's say we're just trading lots of volume, and they actually, like, let's say we apply for like a market maker, and some exchanges will even like say, okay, we will pay you to market make. So you actually make money. So this makes our expected value even more, increases it actually. So this is feasible, but it depends if it's a maker or a taker strategy. And even, for example, in some exchanges, you may not be able to run this even as a maker strategy. For example, Binance, the perps exchange, they strangely say like, okay, if you have a limit order, you pay the same fee as a taker fee. So there is no, you would not make any money there. And then just maybe show what a taker is. So a taker is that you're taking away liquidity, and there'll be, typically there would not be, as a rule of thumb, there would not be, like, because we're trading this on such a short time frame, that the fees would decay the edge to a point where it's like you've inversed it. So essentially what happens is your win values get reduced because the fees really decay the wins, and then the losses get amplified. And typically what happens is your positive EV turns to negative EV. And this is why, for example, this could be, you could do this, but typically as a making strategy. But yeah, we'll I'm not sure if we'll look into making, maybe we'll look into making, but maybe a much later date. So I think that's, okay, so maybe just go over the, so we've gone over the model, we haven't, so the next videos is that we're going to do this, is we're going to look into classification, which is, so we've looked at regression, but we haven't looked at classification, and classification is where we classify into labels, and more specifically, we're going to look into classifying it as a label, like it's going up or if it's going down. And with classification, you get an associated probability. So for example, you get a probability of it, like, okay, what's it, the probability of it going up? And we could potentially use this for our strategy. It's like, okay, deciding when to buy or sell, or anyway, so then once we've gone into classification, then we're going to go into cross-validation and also some back testing, because we haven't gone over some of the back testing performance metrics. So that will be the next part, and then after that we'll go into strategy, where we actually use this model to build a strategy, and there's some very important decisions, and the strategy is also equally as important as the model itself. And so let's do I didn't do exercises last time because I couldn't really think of some good exercises, but this time I do have some. Okay, so some exercises just to build up being comfortable working with matrices. Is to do the following. So the first exercise is to do the dot product, to implement the dot product. And I strongly believe to understand the mechanics is to actually start building your own algorithm for it. So what we're gonna, I'm just gonna copy and paste this code. So, and I want you to write a manual loop. Manual loop to do the dot product, and the dot product is basically you're multiplying x by y. So and to know if you got the correct result, okay, so what we want to do is to pass this test. So at the moment it's false, but that's the code. But obviously don't just, this has to be done as a loop. A few people have posted that, they just pasted this, but yeah, it has to be in a loop. Okay, and then the next one, exercise 2, is to transpose. Okay, and this is quite a common matrix operation, is to transpose. So And to transpose is essentially flipping the. So, for example, you look at the shape, is you're flipping the values of the shape around. But so then I'll just make it more concrete. Is that this is what you want to do? So the shape of it at the moment is 2, 3, and we want it to make it 3, 2. And just in case you're not sure, then what I'm asking you to do is that I've got the example of like what it looks like when it's transposed. So yeah, so then we see, look here, it's false. And then another important operation, and we should be able to do it by scratch, is the Hadamard product. Okay, let me just. Okay, with the Hadamard product, essentially what we're going to do is, let's just assume that we've got our actual values, and then the predicted denoted as y hat. And we want to measure the error, and we're going to measure the error as the difference between them. So essentially what I want you to do is to calculate the error. And why is this not? Okay, here we go. So that I want you to write a loop to calculate the difference between this matrix and that, these two matrices, and this denotes the error, okay? And this is what the values should be. So if we look at the error, then yeah, error is not defined. Oh, because I didn't. So yeah, there's that. I think you may have some issues with like floating point precision. If I do, I'm just going to run it myself. There's a NumPy to factor in like imprecision errors. But yeah, that's roughly the code. Anyway. So yeah, that's the whole video. Thank you for watching, and see you in the next video. Cheers. Bye. This course is free thanks to my paying Patreon supporters. If you're getting value from this series and want to help me create more, please consider joining them on Patreon. You can also support me by buying me a coffee on buymeacoffee.com. Links on my channel details page.